So without further ado, it's a pleasure to have David Reutter is going to talk about on Fusion 2 categories.
Yeah, thanks for the introduction, Chris. So before I start, sort of a quick disclaimer. When I looked at these slides or these notes, I noticed that my handwriting is really bad. I already knew this, but I noticed it again. So if you cannot read something or if something is illegible, please just quickly unmute, say, could you please read out what you wrote there? I can't read it, and that should help us. So I'm going to talk about Fusion 2 categories. These come from a paper I wrote together with Chris, sort of a bit more than a year ago. And yeah, so the basic motivation that we had when we wrote this paper was really sort of trying to understand a bunch of constructions that come from sort of in the vicinity of four-dimensional topological field theories. And so somehow this sort of started as a project in quantum topology. And here I want to understand quantum topology as sort of building linear algebraic manifold invariants constructed via state sums. And the slogan of this game is somehow take certain linear algebraic data and contract it, tensor contract it, according to some finite combinatorial presentation of a manifold. And this finite combinatorial presentation could be a triangulation, it could be a Handel decomposition. And this was sort of done a lot around the 90s. And in 3D, the situation of the state sum was sort of fairly well understood, and sort of by work of Barrett and Westbury in '96. These can sort of all previously defined state sum invariants can usually be summarized as saying you start with a spherical fusion category, and you turn the spherical fusion category into some oriented three-manifold invariant. In 4-dimension, the situation was a bit weirder, but there were sort of much more constructions around. And here's sort of a bit of a table of sort of various constructions that existed. There's this Crane-Yetter invariant, Crane-Yetter-Kaufman invariant that we've heard about a lot in this semester. This takes something which is called a ribbon fusion category and produces some four-manifold invariants from it. There are other invariants. There's of course the Dijkgraaf-Witten invariant that we heard about last week in Mark's talk. And we also heard about in last week's talk that these can be generalized to invariants that actually take as input some homotopy 2 type rather than just a finite group. And these again can then be twisted by Fourier cycles. There was recently a paper by Jean Couy about constructing spherical G-crossed, about using spherical G-crossed pre-diffusion categories to construct four-manifold invariants. And somehow what we set out to do is to say, okay, is this an analogous story to the 3D case, starting with some data, with some linear algebraic data, with some appropriate linear algebraic data, which should look like something like a spherical fusion 2 category, which sort of uniformizes all of these constructions. Now, I started with this, but this is not what I'm going to talk about. Somehow, this is sort of the story on the topology side. And as far as I understand, I think Kevin in his talk next week is going to talk about a universal state sum construction. And this should actually, as far as I understand it, match up in the four-dimensional case. This should sort of be about arbitrary n, but I think in the four-dimensional case, as far as I understand it, should sort of match up pretty well with what we did with the spherical fusion 2 categories. So instead, I'll talk a bit more about the algebraic side of things, why we would care about fusion 2 categories just from a purely algebraic perspective, and sort of where they sit and what they do. So let's sort of switch gears and think about it algebraically. And algebraically, I think the story sort of is organized around finding or figuring out what are good higher categorical versions of finite dimensional linear algebra. And of course, what we've seen on the last slide can sort of be summarized using the perspective of the cobordism hypothesis as saying all of these state sum, all of these manifold constructions, they should really all arise from some fully extended TFT, which goes from the bottom symmetric monoidal n category of n vector spaces. And the question is, what's a good target? Like, what should we take as this n vector, which produces something which looks like finite dimensional linear algebraic? And so let me sort of say briefly that when I say higher categorical versions here, I really mean finite higher categorical versions. There's of course a completely different story as to say what's the appropriate infinity 1 categorical version of vector spaces, and presumably it's chain complexes over this field bounded in degree, and then finite dimensional in each degree. But of course, then there's also the question, sort of what I'm going to answer is what are 2 and 3 and 4 dimensional versions of finite dimensional linear algebra. At some point, there needs to be somehow the push out of these two ideas to get to some notion of infinity n-dimensional versions of finite dimensional linear algebra. But anyways, let's just focus on the finite category number case here. So a question that sort of comes up, of course, is then to say, well, should there even be one of these n-vect guys? Is there a n-vect, or is it just sort of a variety of categories that one could use? And I want to argue a bit on this sort of motivation, actually something like n-vect that we should sort of aim for. So let's look at dimension 2. What happens in dimension 2 is that all sensible proposed candidates for a symmetric monoidal 2 category of 2 vector spaces are either proven or at least expected or believed to have the same fully dualizable subcategory. So some of these sort of candidates could be, for example, algebras over your field and biomaterials and biomaterial maps, or k-linear categories, biomaterial and biomaterial natural transformations. Other examples that come to mind are locally finitely presentable k-linear categories, co-continuous functors, and natural transformations. For that example, it's not yet proven. It's only proven under the assumption that there's a generator, that there are enough compact projectiles. And the fully dualizable subcategory in each of these cases, and this was proven in this paper by Bartlett, Douglas, Schomer, Priest, and Vickery, is the the symmetric monoidal 2 category of finite dimensional semi-simple algebras, biomaterials, and biomaterial maps, which is equivalent to the symmetric monoidal 2 category of finite semi-simple k-linear categories, k-linear functors, and natural transformations. And so this 2 category really deserves the name 2-vect, the 2 category of finite dimensional 2 vector spaces. So whatever sort of notion of 2 linear algebra you start with, if you just look at the fully dualizable things, if you just look at the things for which you get state sums, for which you get fully extended topological field theories, you will sort of be forced to live in this world. And so there's something one could call the best-Jerry hypothesis. I think this name is due to Claudia Scheinbauer, which sort of very roughly goes, and this is of course no serious thing at the moment, but it roughly sort of goes, all reasonable candidates for the symmetric monoidal n category of n vector spaces should have the same fully dualizable subcategory of finite dimensional n vector spaces. And of course, the question is, what is that? What is n-vect? And so let's sort of see at what's known, or what was known at the time this paper was written. We have, of course, the category of vectors, finite dimensional vector spaces, which I just call vect from now on. We have 2-vect, which is the 2 category of finite dimensional semi-simple algebras, or equivalently finite semi-simple k-linear categories. Then what's a good candidate for 3-vect? Well, something that was proposed, and we'll later see reasons why this is a good definition, is the 3 category of multifusion categories. So this 3 category was constructed and proven to be fully dualizable in this paper by Douglas, Schomer, Priest, Snyder. And what I'm going to answer in this talk, or what I'm going to talk about in this talk, is what's the correct candidate for this slot here. What's a good notion of fusion 2 category, which could fit into this slot. So before I continue, before I actually give definition, I think this is a good point to make a disclaimer, which is on this specific question of what's a good notion of high-dimensional linear algebra, there have been some recent very significant advances, I think, by a paper of Reutter and Johnson-Fried. And they essentially, they have a construction which takes some commutative ring, and from this commutative ring, they construct actually a sequence of fully dualizable symmetric monoidal n categories that sort of deloop each other. So it looks a bit like an omega spectrum, but nothing is invertible there. And they can actually produce this 2 category from the sort of abstract machinery. They can start with the algebraically closed characteristic 0 field and produce this 2 category 2-vect and 3-vect from this story, just sort of by abstract nonsense. And I strongly expect, as things are at the moment, but haven't proven, that these fusion 2 categories or multi-fusion 2 categories actually also fit into this story. Okay, so now let's get to actual mathematics, enough of motivation, and let's fix, in this whole story I'm going to fix an algebraically closed field of characteristic 0. A lot of these things can be generalized, some of them get sort of more tricky, so I just sort of stick to that situation. Are there any questions about the motivation? Okay.
Yes, hello, this is Ezra Getzler. Hi. I was wondering if there's a superspace version of your story.
Yeah, so sorry, what
Is there a superspace version, Z2 graded version
Oh, CT, right, okay, yeah.
Because my favorite category is superspaces, not finite dimensional superspaces, not vector spaces, for what it's worth. Yeah.
Yes. Yeah, I absolutely agree. In this setting I sketched down here, you could, rather than starting with a ring, you could start with a category and sort of start building up these sort of higher versions from this category. And then instead of starting with the category of finite dimensional vector spaces as a symmetric model category, you could just start with super vector spaces, and it would produce these higher categories. So from this perspective, these Fusion 2 categories that I'll introduce, it won't be very hard to make them enriched in super vector spaces. But I just focus to the sort of non-super world to sort of get the basic story out.
Thank you.
So right, so let's see what's going on, and let's sort of try to understand this categorification going from 2 vector spaces to 3 vector spaces a bit better. So let's look at this one here. So how did the story go? Well, we sort of convinced ourselves that the good notion of what a 2 vector space, what a finite dimensional 2 vector space is a semi-simple algebra, or equivalently a semi-simple K-linear category. And these two categories are actually equivalent. If you take the category of finite dimensional modules of a semi-simple algebra, you get a semi-simple K-linear category, and every semi-simple K-linear category arises in this way. And similarly, if you look at the bimodules between 2 semi-simple algebras, they precisely correspond to linear functors between these categories. So if you want, you can think of this as some semi-simple version of the Einberg-Watts theorem. And then you get multi-fusion categories by just taking this symmetric monoidal 2 category that we have here, 2-vec, and just taking monoidal objects with duals. So multi-fusion category is really defined to be a finite semi-simple. I should maybe add the word finite here. Basically, everything that I'm saying in the following will always be finite. Take a finite semi-simple K-linear category, add a monoidal structure to it, and require this monoidal structure to have duals. This is what a multi-fusion category is. So for those of you who haven't seen this definition before, let me sort of make a brief aside. When I say fusion category, this is just a multi-fusion category in which the tensor unit is simple. A multi-fusion category I've just defined. And of course, a reason why multi-fusion categories are interested or have been studied other than this sort of high-level abstract perspective is, of course, that a lot of categories that appear in nature do have this property, namely, for example, all representation categories of finite groups, and of course, many, many more examples. And sort of many exotic examples of these fusion categories around that we don't yet really understand. Yeah. So let's sort of look back at this story that I'm sort of sketching here. And let's ask the following. So we want to categorify the story. And we already know this word. Now, this word is a categorification of this word here. So, of course, one way to categorify it would be just to say, let's just take monoidal objects with duals in this word, right? Because after all, it doesn't really matter whether I take monoidal objects in here or in here, since this is an equivalence of 2 categories. And this is roughly, I mean, sort of, this is very paraphrasing, very sketchily, but this is roughly how the story of Gayotta and Johnson-Freed works. But an advantage of passing from this side to this side is precisely this Einberg-Watts theorem, which tells me that while here, the one morphisms are bimodules, and therefore sort of hard to work with. Here, the one morphisms are just plain functors. So on this side, to look at monoidal objects, what a monoidal object will just be some monoidal category whose underlying one category is K-linear and semi-simple, and which has duals as a monoidal category. Whereas here, what a monoidal object would be an algebra together with an A tensor A to A bimodule, which would fulfill various relations. And so it would make it much, much harder to actually work with these gadgets. So here the monoidal objects are monoidal categories with additional, well, with a K-linear enrichment and additional properties rather than some sort of arrangement of data which is more complicated to handle. So what we're going to aim for basically is to first understand what's the appropriate Einberg-Watts theorem for multi-fusion categories. So how can I sort of push multi-fusion categories forward into something which one could think of as finite semi-simple 2 categories. Now, finite semi-simple bimodule categories turn into, and then just look at that's the plan. Here's the plan again. What we're aiming for is an equivalence of this sort. fusion categories, finite semi-simple bimodule categories, bimodule functors natural transformation, into a world where I can think of semi-simple 2 categories, k-linear 2 functors, natural transformations, and modifications. And I pass from the left to the right by taking finite semi-simple modules, and these 2 worlds should actually be equivalent. So that's the start. Once we're there, it's going to be easy how to define a fusion 2 category. Okay, so let's look at some actual definitions. And the way I'm going to present this now is that I'm always going to give the definition in dimension 1 and in dimension 2 in parallel to sort of show you that this is actually, I mean, I'm basically just doing the same things over again, right? And so for those of you who haven't yet seen the definition of a semi-simple category, for example, or multi-fusion category, they'll actually see the definitions now in parallel to the 2 categorical versions. Okay, so let's fix n as either 1 or 2 in this story. And I define a semi-simple n category as a k-linear n category such that, then this is the definition. A semi-simple 1 category is a k-linear 1 category that has direct sums, that is idempotent complete. And for every object A, the endomorphisms of this object actually form a finite dimensional semi-simple algebra. Let me say that there's a variety of different ways of defining what a semi-simple 1 category is. This is sort of the most convenient one, or the, I think, nicest one to categorify. It gives sort of the cleanest sense of where we're headed. So what we are seeing here is basically there are 2 sorts of conditions around. One of them is the local semi-simplicity. This is where sort of the actual sort of linear algebraic meet happens. This is the actual condition. And then there are 2 other conditions which guarantee this Karoubi completeness. And this is what makes the Einberg-Watts theorem essentially tick. This is sort of a completion that guarantees that we get functors on this side here. This is what turns bimodules into functors. And so we have to sort of aim to understand what these 2 notions are. Direct sums is just the usual sort of ordinary way how one would define direct sums in a 2 category. That won't comment on this very much. What's more interesting is what this categorification of idempotent completeness is. This is what I'm going to talk about now.
David, could I ask a question? This is Kevin Walker. When you say direct sums, is that direct sums of both 0 and 1 morphisms?
Yes, so I mean, you already have direct sums of 1 morphisms with that condition. So there's some things that are sort of hidden in that condition. One of them is that this implies that you automatically have direct sums of 1 morphisms, and it implies that you automatically have adjoints to 1 morphisms. So sort of if one would write this a bit more carefully, then you would say it has direct sums for objects and 1 morphisms, and it has adjoints for 1 morphisms. But here you could sort of think of this as just asserting having direct sums for objects, and everything else is sort of captured by this local story. But yes, they do have direct sums for 1 morphisms. Okay.
This might be the same question, but is k-linearity just at the top level? Oh, sorry, this is Aaron Mizelchi.
Yes, k-linearity is just at the top level. I mean, there's this interesting thing. If you say, rather than doing everything just at the top level, k-linear enriched, you want to work internally to vector spaces, say, then you essentially get something like Dot-Kant kicking in, which tells you that you're actually talking about chain complexes, and then you automatically have that everything that you're just you're just going to be in n, n minus, in n, 1 category. So all the higher morphisms will then automatically be invertible. So okay, if you want to have something really non-invertible at all levels, you just have to sort of stick with k-linearity at the top level. Yeah. So I think this is sort of a nice, I mean, right, I don't want to sort of go too much off topic, but I think this is sort of a nice way to think of these, if one just sort of wants to categorify higher linear algebra, there's sort of these 2 variants, like how many levels of linearity do you want to have? And this corresponds nicely to sort of how many levels of invertibility do you want to have? And so you can sort of think of it either way, basically. Okay, so let's talk about idempotent completeness then. And again, a disclaimer here is this was recently generalized to arbitrary n by Gaillot and Johnson-Fried. And Theo also gave a talk about this at the TGFT workshop at MSRI. And very closely related ideas of Scott Morrison, Ken Walker, and also of Kakavell, Winkel, and Sharma. And these ideas, the sort of latter ideas, are in sort of an oriented setting, and this one here would just be for non-pivotal, non-oriented, framed, if you want, in category. Okay, So the very rough idea, and I won't actually talk about the motivation too much here, I just give sort of the idea to get the definition out, is that idempotents in one categories should categorify to something which you can think of as a separable algebra in a two category. Again, if you want to hear more details about this, you should just go and watch Theo's talk. And I just sort of be content with the philosophy and just give you the definition. So let's say C is a one category. Let's first sort of recall something which is of course very well known. If C is a one category, an idempotent is just an endomorphism that squares to itself. A section retraction pair is a pair of morphisms whose composite in one direction is the identity. And of course, then if I compose them the other way around, I get an idempotent. And I say that an idempotent splits precisely if it arises in this way. So precisely if there's a section retraction pair such that the idempotent is sort of the composite of these two guys. And my one category is idempotent complete if every idempotent splits. So our task now is to categorify that notion. And here's our definition that we're using. So let's assume C is already locally idempotent complete. So let's assume that all the Hom categories are idempotent complete. That gives a pretty sort of a nicer word to work in here. A separable monad is a unital algebra object, P, in Hom BB, whose multiplication map admits the section as a PP bimetry map. So this, if you have a two category, which is a single object, such as a monoidal category, then this will precisely match up with the notion of separable algebra. A separable adjunction is an adjunction such that the co-unit of the adjunction admits a section. A separable monad splits if there exists a separable adjunction, such that composing the adjunction the other way around gives you an isomorphism of monads to P. So if I have this adjunction, I automatically get a monad structure in F composed with G. I shouldn't point on my screen with my fingers, that doesn't really work. And you ask that these two monads are isomorphic. And this is just a property of a separable monad. And if we say that C is two idempotent complete, if it's locally idempotent complete, and if every separable monad splits. So for those of you who like to think about these things in terms of pictures, I definitely do like that. Here are sort of the appropriate pictures for that. So a monad is, of course, a multiplication map and a unit on some object P, and it's separable if there exists a sort of co-multiplication map that fulfills these Frobenius-like looking conditions. This is the factor, this is a PP bimetry splitting, and that splits the multiplication. So what we're looking at with a separable monad is something like you could think of as a non-co-unit special Frobenius. An adjunction drawn here such that there exists some section of the co-unit, and this section doesn't need to fulfill any other properties than being a section of the co-unit. And the separable monad separately splits is just saying that if I have this monad, it's actually isomorphic as a monad to this pair of Planck's monads that I can create from the adjunction. And this really gives some sort of visceral sense in which the monad splits. It really splits apart. And so let me make some comments about this definition before I move on. One of them, I mean, this condition of being a separable, admitting a separable splitting, if you're sort of more category theory minded, this is basically saying that the separable monad admits a Kleisli object, or equivalently that it admits an Einberg-Moore object. So from a category perspective, you can do this, every monad determines some lax functor, and this is asking that this lax functor has a limit, co-limit, and actually they coincide. So asking that it's two idempotent complete, you could also just ask that every separable monad admits a Kleisli object, or that every separable monad admits an Einberg-Moore object if you want. So it's really a completeness condition. But it's not just a completeness condition, it's an absolute completeness condition. Because of course, checking that a separable monad admits a separable splitting is really just checking equations. It's not really a universal property. So what we're looking at here is some absolute co-limit. And this also is sort of, this is something which is typical for absolute co-limits, is that co-limit and limits actually coincide in this story. Okay, so let me sort of make one more comment, which is sort of more technical, which is about unitality of P. So in this definition here, I say I have a separable monad. And so in particular, it's a unity. So I have this unit, which is sort of drawn here. And this is something you don't really see with the idempotent, right? So this is somehow sort of a bit of a mismatch between this sort of categorified notion and this uncategorified notion. Where in the idempotent, I do have an equality between p squared and p, but I don't have an equality between 1 and p, right? So this is somehow not really present in this decategorified setting. So there is sort of requiring this unitality of p, and equivalently on the other side of the adjunction, the fact that this actually is an adjunction, that there is a unit of this adjunction, right? Because this unit is what's correspond to the identity of the monad, is sort of a bit of a mismatch between dimension 1 and 2. And this is basically where the Guyot-Johnson-Fried approach differs from our approach, is that they essentially develop a non-unital version of the story. So their condensation monads can then be defined for every n. And right here we call them separable monads, they call them condensation monads. And for n equal 1, they actually specialize to idempotents. And for n equal 2, they specialize to some non-unital version of our separate monads. But in that paper, they showed that actually if C is locally idempotent complete and has adjoints for 1 morphisms, then these two notions of 2 idempotent completeness agree. Because there's some unitalist, you can sort of freely unitalize your algebras and get into this unital world. And since we're in this setting, we're sort of happy to just sort of restrict our attention to unital algebras and unital monads, because it's just easier to work with, sort of maybe more standard, more classic somehow. But that's just sort of as an aside comment if you wondered about that. And the other thing, again, because this is, if you want an absolute limit, it has nice properties, namely you can complete any category, any locally idempotent complete 2 category to 1, which is 2 idempotent complete. And this completion just works by taking the 2 category of separable monads, bimodules and bimaterial maps. And this is an idempotent operation. So if I have something that is already 2 idempotent complete and 2 idempotent completed again, then this is equivalent. So you can always just 2 idempotent complete your 2 category by taking separable algebras, bimaterials and bimaterial maps in it. Okay, so much about idempotent completeness. Any questions?
What is a Kleisli object?
Right, so a Kleisli object is essentially, yeah, so this is, I mean, it's not important for the rest of the talk. It is, if I basically what you write, so where this comes from is this for monads on categories, there's this notion of a Kleisli category and Einberg-Moore category. And if you sort of form a category theory in some 2 category other than the 2 category of categories, this is sort of the axioms you come up with. Is a Kleisli object is the thing that if you're in a 2 category of categories will give you back the Kleisli category. And sort of a way to think of it explicitly is you could say it's I confuse left and right here, so just ignore sort of the handedness, but you could think it's a universal left module, and the other thing is a universal right module. So every module actually factors through this module. So this is about modules of these monads. By module, I really think of in the algebra sense. It's one morphism such that the monad act on it. Okay, so let's talk about semi-simplicity then. So let's briefly recall the definition that we had in sort of an earlier slide. C is semi-simple if it has direct sums, it's 2 idempotent complete, and if the endomorphism of every object is a multifusion category. Right, but if you want to talk about semi-simplicity, somehow one word has not yet appeared, which is the word simple. What does it mean for an object to be simple? And again, now sort of we have set up things in such a way that we can actually give the same definition. So I say that an object X is simple in one of these semi-simple 2 categories if one of the following equivalent conditions holds. 1, this is the usual way of defining simplicity. Every subobject is either 0 or 1 equivalent. Let me actually just give you all of the conditions. Every subobject of this object X is either 0 or 1 equivalent, where I think of a subobject as an object together with a map into X, and I require this map to be fully faithful. So in one categorical sense, I can require this map just to be a monomorphism. In this 2 categorical sense, I require this map to be fully faithful, in the sense that if I unita into it, it will induce a fully faithful map between categories. The second definition is that X is just indecomposable under direct sum. And presumably the easiest definition, if we are over an algebraically closed field, which we are here, is saying, well, in the 1 categorical case, of course, it's saying that, oops, that was not correct, is saying that the endomorphisms of a simple object are just ground field. So there's just the identity in there. And in the 2 categorical setting, we can ask that the endomorphisms of the identity of X are the ground field. Or in other words, saying that the identity on X is actually a simple one morphism in this underlying semi-simple one category, which is the Hom category. Okay, so this is what it means for an object to be simple. And then we can define a semi-simple 2 category to be finite if it has only finitely many equivalence classes of simple objects. So this is again sort of the same story that we will do in the one categorical case. Okay, so far so good. Everything still looks like the one categorical case. Maybe sort of a little proposition with these notions, of course. We want to make sure that this all behaves as we expect it to behave. And it's indeed the case that every object decomposes uniquely up to permutation of summands and equivalences into direct sum of simple objects. So these simple objects really, and these semi-simple categories really deserve the name. So it's really, there's really sort of an aspect of semi-simplicity going on here. And this is about it, about the similarities between semi-simple 1 and semi-simple 2 categories. So of course, the big other thing you should sort of look out for in semi-simple 1 category is Schur's lemma, that between two simple objects, there's either an isomorphism or only a zeromorphism. So if two simple objects are not isomorphic, then they cannot have interesting morphisms between them. And of course, the other aspect of Schur's lemma is that the endomorphisms of every simple object, that the endomorphisms of a simple object are just, if we have an algebraically closed field, are just the ground field. And that's not true anymore. So let's see what we get sort of if we try to get something which is as close to Schur's lemma as possible in this setting. And really, I mean, the reason Schur's lemma, let me give you this sort of as close to Schur's lemma as possible thing. So I just call it the closest thing to Schur's lemma. And the reason this happens is, of course, what Aaron said in his comment, is that we just have linearity at the top level. So we're sort of now one level too far away from the top level to get something like Schur's lemma. But what we still get is this condition, which is saying that non-zero one morphisms between simples have something like a 2 out of 3 property. So if 2 of f, g, and f composed with g are non-zero, then the third is non-zero. And this you could think of, rather than sort of in Schur's lemma, you can show that, for example, if you're not over an algebraically closed field, but any field, that the endomorphisms of a simple form a division ring. And here we don't even get a division ring, we get something you could call like a domainoid, by every where you don't have 0 divisors. But that's like the best you can get, because you're sort of even less than a division ring, you have less linearity there. Okay, so then having sort of these properties, we can sort of start looking at semi-simple 2 categories and trying to understand how they look like, how they feel like. And again, let me do this sort of in parallel to the semi-simple 1 category story. So let me sort of give this sort of sketchy picture of how, in my head, a semi-simple 1 category and a semi-simple 2 category look like. So in n equal 1, what's the semi-simple 1 category? Well, you have your collection of simple objects. Those are the only objects you need to care about. Those are sort of here. And in fact, you actually also don't need to remember endomorphisms. You just know that the endomorphisms of each of these guys is just a ground field. And so really what we're looking at is some finite set. There's not more data in the semi-simple 1 category than a finite set. So semi-simple 2 categories look more interesting. You still have your simple objects, and you still really only need to care about morphisms between your simple objects. So those are my simple objects. But these simple objects now come in blocks or components. So there's no non-zero morphism. So all morphisms between these components are 0. And in a given component, every 2 objects are connected by at least one non-zero morphism. So this you can see from this 2 out of 3 property, which gives you some transitivity. If there's a non-zero morphism from here to here, and a non-zero morphism from here to here, then there also has to be a non-zero morphism from here to here, namely their composite, which cannot be non-zero. So I'm saying this and I'm not drawing the right picture, so now it looks better. And then if you look sort of more specifically, what are these endomorphism categories? Well, this one here, let's look at sort of the endomorphisms of some object. We already have asserted that it's a multi-fusion category. But indeed, since this object is simple, this will be a fusion category, because the identity is actually a simple one morphism. And similarly, these Hom categories, you can think of them if you like. They have NA and NB acting on the left and on the right. They are non-zero, as I just said, and you can show that they're actually indecomposable. So you have these non-zero indecomposable magnitude categories. Okay, and looking at this picture, if you've sort of worked with these things before, I've seen some things sort of with these things before, it becomes fairly clear that what we're looking at here is just the 2 category of finite semi-simple modules of a multi-fusion category. And this is then essentially a theorem we prove that if I have a k-linear n category for n1 or 2, for n1 it's clear, but this is again sort of to highlight this similarity, then it's finite semi-simple if and only if it's equivalent to the 2 category of finite semi-simple modules of a multi-fusion category. And of course, I mean, you can sort of, to go back to the definition, to sort of, you can sort of see where this theorem comes from. I mean, this essentially here guarantees that everything sort of is built from multi-fusion categories. And you actually get that it's all modules you get from this fact that you have this 2 idempotent completeness, so that you actually have access to, if you want, the modules, formally speaking, of all algebra objects in there, which by a theorem, by Victor actually, produces all module categories for you, roughly. So that's roughly what sort of is behind that theorem. Okay, and then moreover, you do have a notion of semi-simple Einberg-Schwarz, which is saying that if A and B are multi-fusion categories, then finite semi-simple A, B bimodule categories, bimodule functors natural transformations are actually equivalent to k-linear functors transformations and modifications. So we've now really managed to have this notion, which is defined somehow independently of the notion of a multi-fusion category, if you want, or you can define it independently of the notion of a multi-fusion category, which is really governed by this direct sum and 2 idempotent completeness, and where the 1 morphisms are now really just functors rather than bimodules. Okay, so then that brings us into a good shape, and we can actually just go on from there and define what a fusion 2 category is. Since I want to talk a bit more about examples later on, let me now, before I sort of move to fusion 2 categories, give some examples of semi-simple 2 categories. Now, of course, by this theorem, we've seen all examples, right? It's just finite semi-simple modules of a multi-fusion category. So I could just give you examples of multi-fusion categories. But I still want to give you some examples to highlight some aspects of this theory. One example is, of course, the 2 category 2-vect itself. So this is a 2 category finite semi-simple k-linear categories, functors, transformations, or finite dimensional semi-simple algebras, as we've seen. And this is a single simple object. And this simple object has its endomorphisms just the monoidal category of vector spaces, and it has a single block because there's just a single object. So that's bit 1. Now we can also look at modules not of a multi-fusion category, but just of a fusion category. And these are precisely the finite semi-simple 2 categories with a single block. Sort of the blocks in a, let me say this in a second, but right, so this could look like this. So there's a single block, there's a bunch of simple objects which correspond to all the indecomposable module categories of this fusion category. And of course, then we can sort of work out what these endomorphism fusion categories are, if you like. And so let me say in a more general multi-fusion category, of course, let me say that all these endomorphism categories that we're looking at here are Morita equivalent, and they're precisely all the Morita equivalent fusion categories that they get from a given fusion category. So all of this information of this block, if you want, is contained in the endomorphism category of a single object. Because all of these guys have non-zero 1 morphisms going this way and this way, so you can compose these 1 morphisms together, get one of these monads on this endomorphism, and can therefore recover these objects from an endomorphism on here. This is essentially, again, this theorem that every module category can be recovered from a separable algebra in the fusion category. Okay, but nevertheless, this perspective sort of allows other ways of looking at these semi-simple 2 categories. Namely, I said before that sort of the first and canonical and easiest and maybe most boring example of a fusion category, or even of a semi-simple category, is representations of a finite group. This is an example of a finite semi-simple category. So we could ask, okay, what's the corresponding thing there? And you can show that, in fact, the representation category of a finite homotopy 2 type, as defined by Mark last week, forms a semi-simple 2 category. So with a finite homotopy 2 type, I mean some homotopy type such that pi 0, pi 1, and pi 2 are finite, and such that all the higher pi k's are 0. So you could also think of this as some finite or essentially finite 2 group void. And representations I can just define as functors into this 2 category of finite semi-simple k categories into 2 vector. And these form a semi-simple 2 category. Okay, so that's it about semi-simple 2 categories. I'd now go on and talk about fusion 2 categories. Are there any questions?
Hi, this is Victor Ostrик. So this last example, this is the same as modules over this pointed category VG omega or something different? Oh,
so this would, yes. So the last examples I'll talk a bit more about these later. But if you take X to be connected, so if pi 0 is trivial, then it's just module categories. Let me get this right. I want to get the counting right. Let's see.
It might depend on pi 2. So if pi 2 is multiplicative group of your fields, then everything kind of matches nicely. But otherwise, I'm not sure.
Exactly. Yeah. Let's wait. Let's wait. That's precisely what I was confused. Let's wait until the next slide. I hope I didn't make a mistake here, but yeah. Let's wait until the next slide because I think I did this computation comes up in a second anyways. So I'll have to look what I did. No, but it should be, yeah. Okay. So let's first look at the definition of a fusion 2 category, right? Because I am later going to look at these as a fusion 2 category. So as I said earlier, now that we have this notion of semi-simple 2 category, we know that the appropriate one morphisms between these semi-simple 2 categories are just functors. So we can now define just a monoidal object in there to be just a monoidal 2 category. And this allows us to make the following definition. A multifusion M category is a monoidal k-linear N category for N1 and 2, such that the underlying k-linear 1 or 2 category is finite semi-simple, and every object has a right and a left to it. So this is all we need in this definition. And the fusion N category is just a multifusion N category in which the tensor unit is a simple object. So let's sort of end this by talking about some sort of more examples of these things. I should say sort of in the paper then, we use this notion of fusion 2 category, define what it means to have a pivotal structure and a spherical structure, and use these to build state sum invariants for four manifolds. But here I want to sort of end with a bunch of examples. And this sort of picks up this example up here. So I think if I talk about these examples, I'll also be able to answer Victor's question. I hope so. So the first example, and this is sort of the easiest, the starting example, an example of a fusion 1 category is just, for example, modules of some commutative algebra. So if I start with a commutative algebra, I get its modules have a monoidal structure. And this gives me some multifusion 1 category, and it's fusion if and only if A is actually just a one-dimensional algebra. Again, I'm over an algebraic philosophy. In n equal 2, I could start with modules of some braided multifusion category. And that will give me some fusion 2 category, some multifusion 2 category. And this is fusion if and only if C itself, this braided multifusion category, is fusion. And in fact, one can show that a fusion 2 category has a single component, has a single block, if and only if it is modules of some braided fusion category. So one way to see this, for example, is I said earlier that if I have a single block, actually it's completely determined by the endomorphisms of every single simple object in there. So I can go to the tensor unit itself and look at the endomorphisms. Now, the endomorphisms of the tensor unit in some monoidal 2 category is some braided monoidal category, because if you want, it's some monoidal 2 category with a single object. And so we know two things. We know this braided monoidal 2 category, which is some braided fusion category. And we know that every other simple object in this block actually arises by taking the modules of some algebra in this braided monoidal category. Right? This is this two-idempotent completeness story. And so we see that this actually just this braided fusion category completely determines this fusion 2 category with a single component. So of course, sort of the more interesting fusion 2 categories are then the ones which have more than one component, where these components sort of interact interestingly with the monoidal structure. So let's give some more examples. So in n equal 1, we can look at the representations of a finite groupoid if we wanted to. This would be an example of a multifusion 1 category. So just functors from this finite groupoid into the category of vector spaces. And this is fusion if and only if this groupoid is actually connected. So if and only if pi 0 is trivial, right? And then it's just representation of a finite group. For fusion 2 categories, I can look at representations of a finite 2 groupoid, as I said earlier, with this sort of functor category that we have here. And this is fusion. This is a fusion 2 category if and only if pi 0 is a point. And now I should be in good shape to answer Victor's question, namely, right, so we first require it to be fusion, so then we just require pi 0 to be a point. So let's see. Okay, I still think about this question because I'm actually not sure what the underlying. It definitely won't be if I start with a 2 groupoid or even a finite 2 groupoid with pi 0 being trivial. It won't be modules of some braided fusion category. So there isn't necessarily a braided fusion category around. It will nevertheless be modules of some multi-fusion category and that's somehow built from pi 1 and pi 2. But I'm not, I'd have to think about it for a second. Maybe I'll come back.
The right way of doing it. Like, I think it should be, if I think about it, a 2 groupoid and the endomorphisms of a 1 morphism, so the endomorph, like endo 2 morphisms, you should have some representation of that group graded via equivalence classes of 1 morphisms. And then this will define a multi-fusion category.
Exactly. Yeah, this is roughly how the story goes. Yeah, exactly. And so it's sort of right, exactly. So you can build sort of this multi-fusion category, and it looks like you sort of squash pi 1 and pi 0 into a single level somehow, which is a bit unnatural. But it's similarly unnatural to how if one would sort of semi-simple 1 category given to you, maybe wrap with some finite groupoid and try to sort of write it as mod of some semi-simple algebra. But I have more examples of this sort later on. So another thing one can do is, rather than looking at representations, one can look at graded vector spaces. So another sort of good source of fusion 1 categories is to say I take G some, right, let me again make it sort of in full generality. Suppose I take G as some finite 2 group. With a finite 2 group, I mean a monoidal group like finite groupoid. So it's a finite groupoid with a monoidal structure such that every object is invertible under the tensor product. And another way to say this is just some 2 groupoid which is connected. So there's a single pi 0. So just sort of to distinguish this notationally, this finite 2 group I call G. So this is G as some 1 groupoid with some monoidal structure, and this 2 type I call X. And then I can again look at functors, but this time from G into K. And this forms something like the monoidal category of G-graded vector spaces. So let me maybe immediately put up this remark. This is sort of most familiar if we assume that G is not some monoidal group like finite groupoid, but then if we also assume that pi 1 of G is trivial, that sort of the top level of G is also trivial. Or in this case, if we talk about X and just say X pi 0 of X is non-trivial, is trivial, then we also require pi 2 of X to be trivial, so that there's only pi 1 of X left. And then we see that what we're really doing here, we're looking at functions out of a group. So then G is just a group, and we're looking just at functions from this group as a set into vector spaces and give it a monoidal structure. And this monoidal structure is essentially induced by Day convolution. And it's inherited from the monoidal structure of G that I haven't yet used when writing. But sort of in most generality, I can do this construction for a finite 2 group. And similarly, one level up, I can start with a finite 3 group, or in other words, a monoidal group like finite 2 groupoid, which I can think of equivalently as some 3 groupoid, which is connected, which is just a single object. And I can again look, sort of ignore this monoidal structure, look at functors, so look just at representations of the underlying 2 groupoid, and then have this induced monoidal structure, which comes from sort of the remaining multiplication on G. And this gives me something like G-graded 2 vector spaces. This is sort of in sort of most generality true about these things. And there's something sort of funny going on, right? And this is fusion if the top level again is trivial. So there's something sort of funny comparing these two examples. They really start from the same data, but for one of them to make them fusion, I sort of have to truncate from the bottom, from pi 0, and for the other one to make it fusion, you have to sort of truncate from the top. And this is sort of a nice dichotomy to think about this. So, and here, these examples, these created vector spaces in the classical case, they can be twisted by some 3-cos cycle. So if I have a 3-cos cycle of this x is sort of PG, or if you want just some group 3-cos cycle, if G actually just happens to be a group, and then you can twist the associator essentially of this monoidal category and get some new monoidal category, and this is called vec G twisted by the 3-cos cycle. And similarly, for this fusion 2 category you have here on the right, you can take some 4-cos cycle of this X, which is some BG, where G is some 2 groupoid, some monoidal group like 2 groupoid, and get this twisted version of 2 vector spaces out. And I should say here that, again, sort of the most classical case is if you assume this fusion condition. So here you would just look at a single finite group, and here you would look at a single finite 2 group if you want. And let me sort of give some more concrete examples of this. So let's look at this a bit more. So let's write XBG again. Again, as I was saying, this is fusion if and only if the top homotopy group of X vanishes. And now we have sort of 2 special cases, right? X has, we assume that pi 0 of X is trivial. We now assume that pi 3 of X is trivial. So we have pi 1 and pi 2. So the interesting special cases are, first one of them is assuming pi 1 is trivial, and the other one is assuming pi 2 is trivial. If you assume pi 1 is trivial, then X is actually just a KH1. So X is just an Einberg-MacLane space. Recover 4-dimensional Dirac-Witten theory if you would build it as a TFT. Or sort of said in another way, what we have is like actual H-graded 2 vector spaces. So we really have a bunch of 2 vector spaces for every element in H. And this 4-cos cycle is an actual group 4-cos cycle for H, and this actually twists the monoidal structure in the way one would expect it to. But sort of course, we could do something else. We could, we make the following other observation is that, right, I mean, the other thing we want to do now is rather than saying pi 2 is trivial, we want to later say pi 1 is trivial. So how can we understand pi 1? Well, if you look at it, you'll notice that the number of components of this category as a semi-simple category is just pi 1 of X. So this actually sort of gets back to your question earlier. If there is a non-trivial pi 1, so if it's not just a group, then you would have you have some non-trivial multifusion category with various components. So the number of components of this guy is pi 1 of X. So if we require pi 1 of X to be trivial, so if we require that X is just in Ka2 rather than in Kh1, then this actually implies that this guy has a single component. It's actually an if and only if. And in this case, we know from what I said earlier that this then has to be mod of some graded fusion category. So only in this case can we expect this monoidal structure to actually come from some graded fusion category. And then it's sort of, right, and then it's sort of clear from this data to see what this graded fusion category is. So let me say which one it is. This guy, 2-vec Ka2 omega, is just modules of A-graded vector spaces. And what's this co-cycle here and here? Well, on this side, we just required it to be a 4-cos cycle of this space, whatever the space is. And in this case, it's a Ka2. So we know that 4-cos cycles for Ka2, this goes back to Juilliard-Street, I think, are just K-valued quadratic forms on A. And they actually precisely classify monoidal structures and gradings simultaneously on the one category vector A. So sort of twisting on this 2 category, in this monoidal 2 category, twisting the monoidal structure corresponds to, in this case where there's a single component, but only in this case, to twisting both the monoidal structure on the grading on vector A simultaneously. And this sort of makes sense. So to make it even more concrete, let's sort of look at these 4-cos cycles, and then we can sort of recover the complete fusion structure from the story. In this case, where A is just a C2. Here we have H4, this gives us a 4. So we have 4 different possible monoidal structures on this fusion 2 category. And here they are. And this is, of course, well known just from the story that it's mod of vect A in, sort of corresponding to the element 0, 1, 2, and 3 of C4. 0 is, of course, just a trivial cocycle, in which case we just get modules of vect C2, of just C2 created vector spaces with no interesting symmetric structure and no interesting grading, just sort of the boring grading. As an underlying 2 category, we know how this looks like. It has 2 simple objects and a single block. Again, all of these have a single block because this guy is simply connected. And the fusion structure maps x squared to x plus x. This, again, you can compute because it's modules of this graded category. So to compute how the non-trivial module multiplies, you just have to take the corresponding. I mean, you notice that this is the same as the semi-simple, the idempotent completion of vector A omega, the 2 idempotent completion, or in other words, it's just algebras, bimetrics, and bimetric maps in vector A omega. And you just have to compute what's the Reutter class of the tensor product of these 2 algebras corresponding to this object X. Now, if I take 1 or 3, so if I take the non-even ones, then I'll actually get, and this is also well known, of course, and I actually get just as a semi-simple 2 category, just a single object, so the fusion structure is clear. But if I take the even one, then this corresponds to modules of supervector spaces, in which case the underlying category, monoidal category, is still vector 2, so I get the same underlying semi-simple 2 category, but now the monoidal structure has changed, because of course, if I take X, which in this case represents the Clifford algebra and squared, this will be Reutter equivalent to the trivial algebra, right? This is sort of complex spot periodicity, if you want. So we see already from this sort of simple example of a KC22 and some cocycling, we get quite a sort of variety of different structures out, right? We have sort of 2 categories we're seeing here, and we have sort of interesting fusion rules we're seeing here. And in particular, this fusion rule looks nothing like the sort of fusion rules we're used to from fusion 1 categories. And of course, sort of the really interesting fusion 2 categories then come in once we have sort of several components, and these components interacting interestingly in the monoidal structure, sort of commuting these components among each other, and then we know that it actually doesn't come from a braided fusion category. Right, and with that, I want to end the talk just in time. And I was planning to have a list of questions, but then I noticed that there are actually so many things about fusion 2 categories that aren't yet really understood that I just want to sort of leave it open and sort of leave it open for discussion and suggestions and ideas rather than sort of forcing some ideas on you. So yeah, thanks for listening.
Fantastic. Are there more questions for David?
Hi, David. This is David Ayala. I was wondering, I was just trying to think through what it means for a k-linear n category to be semi-simple. And there are all kinds of questions that came up maybe you could address, such as, like, in my mind, a first part is short exact sequences, existence of kernel and co-kernel, and semi-simple objects that generate everything. And so each of those notions I understand in the ordinary case. And if you could just say some words about what you have in mind for the higher case.
Yes. So, right. Now, I think I'll again refer to Theo's story, which sort of sorts it out a bit cleaner. I mean, somehow the approach we're taking here is not, if you want, a abelian route. So we're not starting with sort of first figure, like one thing you could do is first figure out what's an abelian n category, and then figure out what are the corresponding sort of semi-simplicity notions on that abelian n category. But another thing, sort of another route you can take is this sort of idempotent completion perspective, where you say there is this much stronger property on finite semi-simple categories, which is actually that all finite limits and co-limits in there are absolute. So are computed just by idempotent splitting and direct sums. So it's all sort of a completely equational theory, if you want. There's no universal constructions you have to ever do. And so you could ask, how do these, like, what are these generating absolute co-limits that you have to care about? What sort of the higher dimensional versions of idempotence and of direct sums? And for direct sums, again, it's clear and it's a thing you would expect. For idempotence, it's sort of slightly less clear, and I think this is sort of been sorted out in the last year. What one should look for. And then you could just say, okay, basically, somehow you want to have something which is idempotent complete at all levels and which has these direct sums at all levels. And then it suffices to make it somehow semi-simple in the actual one categorical sense at the top level, such that the sort of iterated Hom top level categories are semi-simple in the usual sense, and this will then just propagate through and give you all the properties you. I'd be very interested in sort of the abelian approach, but I have no idea and good suggestion of what an abelian category should be.
I see. So can I summarize that as it's like kind of each one categorical tier at a time, you demand idempotent completeness and direct sums, and that would be a first guess, and that works. Plus the semi-simplicity or demand at the top. Gotcha. Thanks.
David, this is Victor Ostrich again. I'm wondering what kind of monoidal categories you expect to obtain as decategorifications of these fusion two categories. So I mean, I assume that there is some kind of decategorification here.
Yeah, that's an interesting question. So what's right? So for fusion one categories, you
for fusion categories, answer is based rings, something like this, and kind of.
So we recently sort of started looking into this actually. You get something which is, if you just you get something which is definitely a multi-fusion category. So if it's
that's kind of so you have, for example, you have this equality x squared equals to x plus x.
Right. Yes. So
this cannot happen in multi-fusion category. So that's
so it's not quite a fusion category. It's idempotent complete. Its idempotent completion would be a multi-fusion category. So it's something which is like a non-idempotent complete version. And then there's some baseness. I mean, then there's also these one morphisms are not just arbitrary vectors, they're like specified simple one morphisms. So then there's also some basis. So I mean, short answer is I don't entirely know, but it matches. I mean, it matches nicely. So if you think of these base rings first, you could say I ignore the basis, then it's just some semi-simple algebra. I think that should correspond to if I ignore the basis, it's something that at least once I've idempotent completed it will give me a multi-fusion category. But somehow it's important that you haven't actually idempotent completed it and that you still remember the spaces if you want.
Yes.
It's
like multi-fusion category in which you remember some decomposable objects, which are kind of bases.
Right. Exactly. And somehow even sort of remembering, and even remembering the uncompleted version of it somehow.
Interesting. Thanks.
Yeah, I think this is an interesting sort of direction to sort of figure out what's going on there. I mean, something else we've sort of been looking at, which is very much along these lines, is sort of trying to see what is a good notion of Frobenius-Perot dimension of Frobenius-Perot theorem in that setting. Sort of what should one aim for? What are the sorts of things one would expect? But this is all still a bit unclear, but it gives some nice structures, I think.
So I have a question, Dave. This is Corey. So kind of following up on Victor's question, if you do take that base ring you get where you just take, equivalence classes of bimodule categories, of one morphisms, you get some base ring that doesn't look like a fusion ring, as Victor was pointing out. Can you say what kind of properties that ring has? Like, is that ring itself, is that when you complexify it, is that semi-simple, all these kind of things?
Right. I mean, you can sort of do two things. One of them is what I said earlier, where you say you take the following one category whose objects are the objects of your original fusion 2 category, and whose Hom 1 categories are just the K0 of the Hom semi-simple categories. So that will give you this sort of multi-fusion-like thing, which is sort of an uncompleted multi-fusion category. But you can do something, I think this is what you were suggesting, where you take even less information, where you just say, let's do it sort of more, and let's just take the ring, which is generated by saying, well, for example, just say it's the free abelian group generated by the equivalence classes of simple objects, and its monoidal structure there. This is like less information. I think this ring is I think that the real thing one should look at is this sort of this monoidal category rather than this ring, where you have also these where you remember these Hom set modules somehow. If you forget this information and just look at the sort of ring freely generated by the simple objects, then I think it's a ring with a set basis, but for example, it won't be transitive in the sense of your book, for example. So it will not behave right. It's a ring. It has a basis, and the coefficients of the multiplication under this basis are positive integers. But you don't like duality looks weird. And the reason duality looks weird essentially is that what happens, for example, what happens in this case, this X is actually self-dual. So it is the case that X and X dual, right, is the same object. But the way the co-unit works here is that you go from X tensor X, the splits is X plus X, but there is a non-zero one morphism from X to I. So the co-unit will just take this, go into one of these components, and then from this component go into I. So you don't sort of, on this level, you don't actually see this duality, which makes sort of the fusion ring well behaved. And to see this, you have to sort of include the information of the one morphism. So I think the sort of more natural gadget to look at is this monoidal one category, which you get as a decategorification, rather than sort of twice decategorifying. Right.
This is
sort of the moment you forgot connectivity, you've sort of killed too much information, basically.
Hi, this is Alex Bolivan. I'm interested in have you thought much about like the relationship with Hopf categories and fusion 2 categories, like in the sense of like the Byers neutral work?
Yeah. Right. So I would lie if I said, I can give you theorems, but sketchily, of course, what you would expect that if you have a Hopf category whose underlying one category is simple, then if you take its modules, you'd get a fusion 2 category, or multi-fusion 2 category at least. It shouldn't be actually a fusion 2 category. That should be, depending on the axis. Of course, shouldn't be too hard to see, because you start with the semi-simple. First of all, right, you'd start with this Hopf category. I guess you'd also require the underlying monoidal category for Hopf category to be a fusion category. So you take MOPS, so you get a semi-simple 2 category, and then the co-multiplication just gives you the monoidal structure. And there's not too much, there's no problem with that, because once you have a monoidal semi-simple 2 category, you're almost there. You just need duals, and that's the Hopf structure.
And would you expect all of the fusion 2 categories to be equivalent to a module, like the bi category of module categories, over a Hopf category?
That's a good question. I would say I'm not confident enough to make any claim along these lines. I think it's possible.
No, that's
situation one I mentioned below suggests not, but I think it's quite possible in this dimension.
Thanks a lot.
Hi, this is Arun. I had some maybe slightly different question. So in the world of fusion 1 categories, given a finite group G, you can build 2 fusion categories. One is rep G and one is vec G. Mm-hmm. And I remember learning there's a Morita equivalence between these two. And so they both give you untwisted Dirac-Witten theory. Do you know if that's still true if G is a 2 group and we're looking at the corresponding fusion 2 categories?
I would expect so. And again, I think that should follow there should be formal reasons why this follows, but I can't tell you on the nose what these formal reasons are at the moment. But yes, this you definitely expect it. There's some, with this equivalence, there's some interesting sort of level shift happening, because somehow if you look at rep G, what rep G sort of wants to be is, the underlying groupoid X has just pi 0 X is trivial, and pi 1 x as g. Whereas here you want to think of it as having pi 0. Let me make sure I'm saying the right thing. Well, okay, it's the same. Anyways, yeah, all I want, right, okay. Okay, what I'm going to say is more trivial than I hope for it to be. But basically here you're really using bg, whereas here you're using g, right, as factors out which you take. So there's some level shift why the g sits. I hope this wasn't, right, there's like a difference here in using g and x here. And similarly, one level up, you have sort of these two groups, and in one of them you have pi 1 and pi 2, and for the other one you have pi 0 and pi 1. Which you want to sort of shift over.
Okay, thank you.
Fantastic. Well, if there are even more questions, we can continue discussion in the tea room. I'll put the link in the Zoom chat. There it is. So everyone is welcome to hang out there. And let's thank David again, virtually.